Hey everyone, Geography Instructor Anne Saxe here. And in this video, I'm going to be talking to you about atmospheric pressure and wind. And the information is coming from McKnight's Physical Geography textbook. If you're using that particular textbook, you can follow along in Chapter 5. How could we describe the nature of atmospheric pressure? First, we need to know that air is always in motion. We may not sense it and we may not always feel it. And sometimes we wish we could feel it more in my situation because I'm recording this video in July in the Nashville, Tennessee area, and we sure could use a lot more breeze. But even if you don't notice it, the air is always in motion. And this is caused by unequal heating in the atmosphere. As we know, locations on the Earth are different temperatures. Some are warmer, as in near the equator, and as you progress north and south toward the poles, by and large, temperatures get colder, with a lot of variation in between. And it's this difference in temperature that creates differences in pressure, and that difference in pressure is what causes the air to move. And air will always move from high pressure to low pressure. I will probably repeat that multiple times in this video because it's very important to remember the direction of airflow. When we get to the more complicated weather processes, you will always want to go back to that basic to understand the movement and direction of air. It moves from high to low, not the other way around. And we can break down our winds and examine them at different scales. If you live near a sea or an ocean, you might have land and sea breezes that shift over the course of the day. Or if you're in a valley or you live on a mountain, you might experience mountain valley breezes that change over the course of the day. And then, of course, we have our global scale winds. And that's what we'll be focusing on primarily so we can understand broad weather patterns. Winds like the trade winds and the westerlies. Before we get to that, though, we need to understand some basics about atmospheric pressure. The atmosphere constantly exerts force on every surface. And I find this fascinating. We tend to not feel it because our cells are adjusted to having a certain amount of air pressure, which is coming at us in all different directions. It's not like we just have this column of air pressure on our head, but it does come at us from all different directions. And as you can see, it's as if you took a cube, projected it out to the very top of the atmosphere, and depending on whether you're at sea level or you're at elevation, you will have a certain amount of pressure pushing and exerting its force in all directions upon you. Now, you can see this in action when you see an astronaut return from a space mission where there is no gravity to pull this atmospheric pressure toward the surface. And their muscles atrophy relatively quickly, and that's why they have to keep exercising, because they don't have the force of gravity and atmospheric pressure to keep their muscles strong and toned. On average, at sea level, the force of the atmospheric pressure is about 15 pounds per square inch. As you increase your altitude, you'll see that pressure will rapidly decrease. So the lower pressure you can see in this diagram here, lots of molecular activity and higher pressure. But as you get higher up into the atmosphere, the molecules are spaced out more, and so the pressure decreases. And again, that's because you'll have less atmosphere above you as you get into altitude. You can see that too in this table, where at 0 miles of altitude, the pressure above you, or the atmospheric pressure, is 1,013 millibars. But if you go up to 11 miles of altitude, the pressure is only 76 millibars. And we know this too from when we fly on commercial airplanes. The cabin pressure is set to keep us comfortable. And they talk about if there's a sudden drop in pressure, then you have to put on your oxygen mask. Small changes in elevation can produce significant changes in pressure. Another example here that I'm thinking of is if you cook something at sea level, you will have different instructions than you will have if you are trying to cook something at altitude. How do we measure atmospheric pressure? Now we'll apply this less to us personally, but more to the atmosphere and how we use pressure and measure pressure to try to understand and make predictions about weather and climate. You have probably heard on your local weather that the pressure is measured in millibars, or they talk about the barometric pressure. At sea level, it's 1,013.2 millibars. And this device here on the left is a barometer, which is typically used to measure the force or the surface area air pressure. This is very useful information to meteorologists, and climatologists, because we can use our atmospheric pressure measurements to sketch some isobars on a map. And the isobars are, if you think of an ISO, anything with an ISO in it, you could connect lines of something that's equal. So isobars are connecting lines of equal atmospheric pressure or millibars. Isotherms connect points of equal temperature, and so on. But in this case, an isobar measuring the atmospheric pressure helps us to identify high and low pressure centers. So here we see the millibar at 1,020 is our highest reading in this case, and 996 millibars is our lowest reading. And that helps us to identify high and low pressure centers. As we said, air moves from high to low pressure. So we really want to differentiate or identify, I should say, these high and low pressure centers, because then we can make some predictions about the movement of air, winds, storms, etc. So again, your isobar at 1,020 is the highest pressure reading on the map. So we then designate this as our high pressure center. And 996 millibars is our lowest pressure reading on this map. So that gives us our low pressure center. These are called, another way you might hear it referred to in the weather is a ridge or a trough. High pressures form ridges. So here, what's a ridge? It's an elevated feature. What's a trough? It's a feature that kind of forms, it may form a U shape, but it's a depression. So if you think of a high pressure ridge, if you think of gravity, or if you want to try to remember that air always moves from high to low, you might think about ridges and troughs. Where is something going to go? If it's a high, it's going to drop down to the lower elevation. So that might help you when you try to remember the movement of air. Again, this creates our pressure gradient, the differences in air pressure. Air will move from or at a right angle to the isobars that were created on the map. So here again, you see a lot of activity excitability among the molecules, and that's going to cause them to move to lower pressure. And it doesn't move, say, this way along the isobar map. It's going to move perpendicular to the isobars as it moves from high to low. So you can already start to see how or what direction the wind would begin to move. We can identify with our isobars weak pressure gradients. And here we have a lovely day sailing. You see that the wind is blowing and it's keeping those sails up, but it's not tumultuous at all. And this indicates a weak pressure gradient where the distance between the isobars is great. So down here on this diagram, you notice that at 1,008 millibars, the distance between this isobar and the 1,012 and the 1,016. By the way, isobars always go up in fours. Typically, that's what we see. In intervals of 4, I should say. So from here, actually, this is the high, and we're getting out to the low. So from here out, the gradient will be slow. The winds will be slower and calmer. But where the isobars are close together, we have what's called a strong pressure gradient. And there, the distance between the isobars is small, so pressure is dropping more dramatically. And that's going to give us some strong winds like these folks here are experiencing. Now, this makes a lot of sense to us, and we would think, okay, great, I get it now. Air moves from high to low, and so now I can look at wind patterns and understand how things move. If only it was that simple. If the Earth didn't rotate, that's exactly what would happen. Air would just move directly perpendicular to the isobars, high to low. But the Earth is rotating, and that gives us something called the Coriolis effect. Now, I do find this concept to be one of the more challenging concepts for students. So I encourage you to, you will have, and if you're in my class, you will have some videos that will help support your understanding of this. But the Coriolis has winds as the Earth is turning. The winds will, if the wind was just moving in, let's say you have a high pressure here, a low pressure here, and wind was just moving from the high to the low, that's what we would expect. But you throw in a little rotation of the Earth, and now that air is deflected to the right in the northern hemisphere. So it gets things a little more complicated. In the southern hemisphere, it's the exact opposite. Your winds would move from high to low, but with the Coriolis effect, it causes winds to deflect to the left. All right, here you see what it looks like on an isobar map. Again, we would expect winds to just move from high to low, but we throw in the rotation of the Earth and it causes the winds to become parallel to the isobars. And when you combine that, the pressure gradient force and the Coriolis effect, we get what's called a geostrophic wind. So you have the Coriolis effect, the pressure gradient, and now we're going to throw in another variable that will influence the direction of wind, and that is friction. So friction slows down, as you might expect, the wind movement and reduces the Coriolis effect. Here we see winds in the upper atmosphere moving freely. In the lower atmosphere, however, you have a lot of turning twisting, spiraling because of friction at the surface. And we will notice that here, as we saw in the previous slide, the Coriolis effect would cause, if we didn't have friction, would just cause this air to move parallel to the isobars. But now it is a little bit more parallel, but still with that curve. And again, this is at closer to the surface in what's called the friction layer. So now our wind is crossing the isobars somewhere between 0 and 90 degrees. This will help us then start to understand weather processes. Now that we've put the pressure gradient, Coriolis effect, and friction together to understand that it makes our predictions a little bit more complicated, but we do have the ability to predict wind flow patterns and how they will develop around high and low pressure centers. Low pressure centers, again, are those depressions or troughs. Low pressure centers are also called cyclones, not to be confused with hurricanes or what in Asia might be called a cyclone, which is an equivalent to a hurricane. Here we're just talking about low pressure centers, and that could be any type of storm. In a low pressure center, called the cyclone, we have air that spirals inward and upward. So it's coming out of the high, but this is a low pressure center, so air is moving inward toward the low. And it's also spiraling upward, as we'll see shortly. We have the opposite happening in the southern hemisphere. We have to always mention, because if you were trying to analyze weather patterns in Australia or something like that, you would be very confused. High pressure centers, or anticyclones, spin in the opposite direction. So this is a high pressure center where air comes out and it's moving toward the low. So since it is moving out, we know it's diverging as it spins out toward that low. And that's in a a clockwise direction in the northern hemisphere. Cyclones in the northern hemisphere move in a counterclockwise direction. Finally, let's take a look at the vertical movement of cyclones and anticyclones. Now that we know this air coming and diverging out of a high pressure anticyclone is going to be moving toward that low pressure. And then it will be, the air will rise for reasons that we'll talk about in the next video. And as air rises, it cools. And so you need this rising and cooling mechanism in order for clouds to form, which can then produce precipitation, whether it's in the form of rain or snow. So we typically associate low pressure cyclones with cloudy or rainy or stormy conditions. High pressure centers, on the other hand, have descending air. As air descends, it warms. So we tend to associate anticyclones or high pressure systems with fair weather. This will be really important to remember. High pressure centers, descending air, fair weather. Low pressure centers or cyclones, rising air that can produce, not always, but it can produce clouds and precipitation. So I hope this video has been informative for you in understanding air pressure. Thanks so much for watching. And in the next video, I'll be talking about global pressure and wind patterns. Thanks so much for watching.